So I thought I'd end our sort of discussion of pipes and complex networks by just showing you how quickly this becomes complicated, so that we can get a sense for it. You can solve these problems, once you set them up. It is just algebra. You can solve them with a computer, or with some other, even with like an Excel spreadsheet. But they very, very, very quickly get very, very complicated. So we'll just take a look at this somewhat more complicated problem. This problem, compared to the last problem, we have three pipes in the branching network. We got A, B, and C here. We've got an inlet pipe that is non-trivial in length, so we don't know the pressure right at the junction here. We know the pressure at the inlet. We know the pressure at the outlet, but both are separated from the junctions by significant lengths of pipe, L2 and L1. The problem has therefore a lot of different diameters. It's got the diameter of this pipe 1 section. It's got the diameter of the pipe 2 section, diameter pipe A, diameter pipe B, diameter type C. In addition, we're going to assume that there's not a significant height change. That would just add more complication. But we're going to look at all the places where we're going to have loss coefficients. So even if we assume there is no loss coefficient at the inlet, that's probably, we could assume that that's not a problem. But we would have a loss coefficient here. Let's call that K1 because there's going to be a branch there and the fluid going up there is going to experience a loss. Similarly, there's a loss coefficient there, which I'm going to call K2. So this is the loss coefficient for the fluid that goes straight through the junction, but nonetheless, there will be a loss coefficient because we know there could be recirculation zones as it goes through these cross channels. We're going to have K3, of course, the fluid that comes down here and goes downward on the joint in that junction. Of course, we're going to have all these corners. Before we do the corners, let's do the same thing over here. Sorry, just keep my numbering scheme the same as I had. So we're going to have this where it's entering the junction here is going to be K4. Entering the junction here could be K6. And entering the junction here could be K5. Again, could be recirculation zones as they go past these sharp corners causing losses. There's of course going to be all the corners now, right? So we've got these sharp corners are all going to have significant losses. So K7, we'll call this one K7. This one will be K8. K9 will be down here in this corner. And K10 is here. And finally, there could be an exit loss here of K11, depending on how the exit really works. So those are a bunch. I'm sorry, no, K11 isn't the loss. We're going to put K11 here. Sorry, I changed that. Get rid of this. We're going to assume there's no losses at the end. Doesn't matter. We can add a K12. But anyway, let's say it's just a K11 right here as it kind of all goes through this sharp corner into that final stretch of pipe. So even assuming that there's not anything happening at the inlet or the outlet, we have a lot of loss coefficients there. I'm not going to give them values. That's not the point of this. We're just going to write down what the equations would look like. So what we know is that the inlet pressure to the first junction, we're going to need to label this junction. I'm going to label the pressure at that junction P1. I'm going to label the pressure at this junction P2. So we don't know those pressures. They exist. They're going to be shared by all the pipes that are leading into that junction. The pressure at the inlet minus the pressure 1 is equal to L1 over D1 times F1, 1/2 rho U1 squared. So that section really just has, as we've drawn it, it just has maybe, frictional effects. You could argue there might be a loss coefficient as it enters this, but we're going to assume those are taken care of by the exiting parts of it. P1 minus P2, so that's the junction to the junction. That's going to be the pressure drop for all three of these pipes in the pipe network. So the first one would be, 1/2 rho UA squared times LA over DA times FA plus 1/2 rho UA squared K1 plus K7 plus K8 plus K4. And then we also have P1 minus P2 is equal to 1/2 rho UB squared. LB over DB times FB plus 1/2 rho UB squared times, which K's do we have there? K2 it looks like, and K, can't read your handwriting, K5, that's supposed to be a 5, I think. Yeah, K4, K5, that's a 5, plus K5. And then P1 minus P2, that's a 2, is also equal to 1/2 rho U C squared, LC over DC FC, plus 1/2 rho U C squared times the K's in that loop. So that's K3, K9, K10, K4. K3, K9, K10, and K4. All right, we've got plenty of equations. Then we got to go from pressure 2 to pressure 0. So P2 minus P0 equals 1/2 rho U2 squared L2 over D2 times F2 plus 1/2 rho, that's a rho, it looks terrible rho, U2 squared times K11. So those are our equations for the pipe flow. How many unknowns do we have? We know P in, that's not an unknown, and we know P out, that's also not an unknown. We know the lengths and the diameters, we assume, and the densities. We don't know any of the velocities. So the velocities are all unknown. So we have velocity unknowns of U1, U2, U3, I'm sorry, not U3, UA, UB, UC. So we have 5 unknown velocities. And we have 2 unknown pressures. We don't know P1 or P2. That was, we don't know the junction pressures. So we have 5 unknown. We have 1, 2, 3, 4, 5, 6, 7 unknowns. 7 unknowns. How many equations do we have? 1, 2, 3, 4, 5. We only have 5 equations. So we know in advance that we can't solve this. Now you can say we also don't know any of the F values. That's true. But if we knew the U values, we would know the F values. So that's not an additional unknown. That's just the fact we still don't know U. So that doesn't add to our unknowns. But we do legitimately have 7 unknowns. And so we need more equations. So where are we going to get those? Well, we haven't used mass conservation yet. So we're going to get a couple more equations using mass conservation. So we'll say that m dot 1 has to equal m dot A plus m dot B plus m dot C, right? Because that's the mass flowing in pipe 1 has to supply the mass to all 3 of these pipes. We also know that m dot 1 is equal to m dot 2. So that's 2 more equations. So now we have 7 equations and 7 unknowns. So in theory, we could solve this, right? So here we go. This is a soluble system, I think. It has 7 equations and 7 unknowns, but it's complicated. These aren't complicated. These K1, K7, K8, these are all things you just look up. These are just numbers. You're just going to plug these in. These are just going to turn into numbers. But you're still going to have a complicated system of 7 equations and 7 unknowns that you have to manipulate in order to solve. It's just algebra. It's not, mathematically, it is not hard in the sense of being mathematically sophisticated, but it is kind of a mathematical grind. And that's the case for even this very, really very simple system. It's just a pipe, goes into 3 pipes, comes back to 1. Kind of thing that could happen in any heating system, even a part of a heating system. So these systems can be very complicated, and obviously, but you now have the tools to solve them. You just need to figure out ways to solve large systems of equations like these.